Alright, so today we're going to be doing day 12 in Advent of Code. Today's challenge, we get another grid, and this time it's a garden which has different types of plants or flowers, and each type of flower or plant has a specific letter. So there's A's here, there's B's, C's, D's, and E's, and so on and so forth. And if they're right next to each other, then they're counted as a group. So all of these A's, they touch either horizontally or vertically, not diagonally. Then they become a group. So these B's over here are a group of 4, and what our task is to figure out how many fences we need to enclose all of these different areas. So here's an example of how many fences we would need. So we would need 4 from the bottom, 4 from the up, and then 2 on each side of the A group. And then we would do the same for B, for C, for D, for E. So this is how many fences we would need, and we just add all these numbers together, and that is going to be the perimeter, right? And once we have the perimeter, we multiply it by the area, which is how many different plants are in the specific group, and then we add all of those numbers together, and that should be the result. And we have some examples here. So one thing to keep in mind is, even though that technically these here and these here are touching, they're just a bit far apart for the example. So here the A's and B's are touching, then there's still gonna be a fence edge for the A and a fence edge for B. So we still have to put 2 different fences in between here. So that's good, because we don't have to check where the fences kind of connect and then minus them out so that there is not 2 of the same fence. So it's just actually simpler to calculate it like this. If we can just keep track of all the fences here. So to solve this, we will get the input file, which is this is how it looks right now. And we will go and put it in the input.txt. And I will include it, import it by opening it and then making a map of the garden map. And then to solve it, what we want to do is to keep track of the total price, and the total price will be the area times the perimeter of each different region. So we iterate through all the regions, and we find all the regions from a function find regions. We get the area, we get the perimeter, we multiply it, we get the total price, we print the total price. So firstly, how do we find the regions? To find the regions, we have to know how many rows and columns we have, and we can get this from the garden map easily. We have to have a visited cell so that we know that we haven't seen that cell before, and we make it a set so that there is no duplicates. And we have to have a list with all of the regions that we found. So what we can do is we can do a depth first search with the starting row, starting column, and the crop type. And we do this because if we have a starting position, if we do depth first search on it with a stack, we can just keep adding to the stack until we do not find any more alternatives. So what we will do essentially is we will start at A, and we will look upwards and then to the right and then down and then left and see, okay, is there another A here? If there is another A here, then it means that it's part of the same group, they're touching. And then we add this to the stack, so this will be the next thing that we look at. Then we look in each direction, we try to find other A's, and so on and so forth. So let's say we find this one, then we find this one, and then it will check all of the other directions. So it will go depth first in, and this is because we're using a stack. If we use the queue, this would be a BFS implementation, but it would work both ways. It's just I prefer to use stack. So once we use the stack, we have to pop what we've just used so that we don't use it again. And of course we will append the new ones once we find them, and we add it to the visited cells as well, and we iterate through different coordinates, and these are the up, down, left, right coordinates for delta row and delta column. We check, of course, if it's not out of bounds, and then we check if the crop type at that specific coordinate, so the neighbor row, which we just got from the new coordinates that we added, we check if it's the same crop type and if it's not in the visited cells. So we shouldn't have visited it already, otherwise why would we add it? But actually if we take this away, it would be okay, because this is a set, so there would be no duplicates anyways. once we have gone through the entire stack, so once we've gone all the way through and we found all of the A's, and then eventually we popped everything from the stack because there was nothing left to search, then we return the current region that we found. And this is when we call depth first search. And we call it for every row and every column, and if it's not in the visited cells. And we also append it to all of the regions once we find the new region with depth first search. So we will have all of the regions, which we can iterate through once we get it from find regions. Then to get the area of it, it's pretty simple. We just have to return the length of the region cells, because we just have to count how many cells there were. So if there's 1, 2, 3, 4, the area will be 4. So just how many different elements are in that region. But for the perimeter, it's a bit more difficult. What we have to do is give it the region cells and the garden map, and we do the same thing with the rows and columns, and we iterate through rows and columns from the region cells. And what we're checking for here is if in whatever direction we're checking, so right here we get the garden map, and I do r-1, so we take the row and we go -1, so upwards. If it's not the same as wherever we are right now, meaning at this index, whatever letter we find, so if we look upwards and if this letter is not the same as this one, then we add 1 to the perimeter. If it is the same, then it means, guess what? It means that they are part of the same place, the same group. So there should not be a fence here. So that is why we do not add 1 to the perimeter. But let's say if it checks to the left here and there's a B, then this is not part, so there should be a fence here. So that is why we add 1 to the perimeter. And we also check if R is 0 or if R is rows -1. This just means that when we reach the boundary, so if this is the entire boundary of the map, then if there is an A here and it checks here, of course there's not going to be anything, so there should be a fence on the edges as well. So we do this for every direction, up, down, left, and right, and we add 1 to the perimeter every single time. So we can get the perimeter for each region. Once we return it, then we multiply by the area, we add it to the total price, and we return it. We print it. So if we print it, we can see here, we have 1,480,000 something thousand. And if we look at the answer for part 1, that is the correct answer. So now for part 2. The elves have discovered that there is a bulk discount apparently, and what that means is that for every instead of calculating the perimeter, we can calculate how many edges there are. So in this example where there's some E's and X's, there are, how many does it say? 12 sides. So there's the side on top, so this entire thing counts as one side instead of 1, 2, 3, 4, 5 edges. One side, 2 sides, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is 12 instead of, I don't know, 30 something probably edges. So if there is a perfect square, even if it's 10 by 10, it will not be 40 edges, it will be just 4 sides. So when we multiply the sides by the area, it will be cheaper for them to buy it, because that's supposedly the price of the fence. And we get some examples here. So we just have to think about what kind of different shapes could happen. So if we have something like this, some very confusing shape, then this would be 1 edge, this would be 2 edges, this would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the more complex the shape gets, the more edges we get. But basically what we're going to be interested in is, once we get the edges, if I can show you. So in part 2, everything is basically the same, except what's it called? Find regions is the same as well. Get perimeter sides is a bit different. So the only thing that I've done different in this one is, instead of just adding it directly, where is it? Adding it directly to the perimeter, what we do is we add it to a fence coordinates. So every time that we check a certain direction, if we know that it is going to be a fence, then we just add it to the fence coordinates. So in Paint here, we will know that, okay, these will become fences. And we save these coordinates as fences. And later, when I go through each different coordinate, because they're still edges technically, they're not sides, I have to check, okay, are they next to each other? And if they are next to each other, then make this into a single line and add just 1 point for this, one side. So once I've added this to the fence coordinates, we can get the fence coordinates and send it to the fence two sides. So it takes whatever fence we gave it, and then it transforms it into sides. And we do this by checking, okay, what direction is it in? And we have to keep the direction, because if we imagine in this space right here, for example, or in this corner, so if we say that the edge is towards the middle, so if the edge is here in this specific point from this side, but there's also this edge here, which is in this coordinate, then these two will be in the same place. So what we want to do is to keep where it's coming from. So this one's coming from up, it's coming down, this one's going towards the right, that's where the fence is. So we want to keep the directionality of it. And we did that when we added to the fence coordinates. We added the row and the column, and if it's facing upwards or downwards or left or right. So we keep that in the information. Then we see which kind of a row and column we got, if it's facing upwards or downwards or left or right. And we add it to the neighbor rows and neighbor columns, depending on what they are. Then we get the edge row by adding the current row and the neighbor row. So if this is the current row, and let's say that this is a neighbor here, then if this is 0, 0, and this is 0, 1, then this would be, this right here would be 0 and 0.5, right? Just right in between. And the reason that we have this is to see exactly where it is, if it's in between two different things. And we can also determine if it's vertical or horizontal with this. And we do it by checking here if the edge modulus 1 is equal to 0. So if there's no remainder, then it means that the segment midpoint is vertical. Since it's an integer, not a float, it doesn't give us a remainder. So that means that we're going to explore up and down. And we do this for each edge and direction and edges, of course. And we don't only explore up or down, but also left or right. So this is what this if statement is for, and this is what this else statement is for. So if we somehow found this edge right here, we want to both explore this way and this way, because we don't know. Maybe the one that we found right now is somewhere in the middle. We don't know if it's the corner one. So we have to explore all the way to the left until we find the end, and all the way to the right until we find the end. So this is what we do. We make a for loop to explore in the -1 direction and the +1 direction. In this case, delta row will be added to the edge row, and in this case the delta column will be added to the edge column, because we're going vertically and then horizontally in the other case. And we find the next edge, and we just make a while loop while the next edge is still in the same direction. So while this thing was still stored that it's upwards, this one is upwards, upwards. That's how we can know it's part of the same edge, part of the same side. Then we keep going, we add it to the current row until we have found all of them. And then we find the edges, the entire side, and we store it together. And we have to add it to the visited edges as well, so that we don't visit it again. But once we've done all of this, so for all of the edges, then we can return how many sides we have found. And we do side count +1 only every time that we enter in here, so that we don't add it for every edge. We add it for every side, of course. Then we return it, we multiply it by the area again, and we get the total price for every region. And if we run this, 899,196. 899,196. So that seems to be the correct answer. And now for the time complexity of part 1, if we scroll all the way down, everything is O of n, which is nice. So there's no really complex parts where we have to iterate through the same part in the map several times. So the time complexity is O of n, and the space complexity is also O of n. And actually, it's the exact same for part 2. So the solution shouldn't take much longer, even if we had a much bigger input file, which is good to know. All right, so that was day 12. If you guys want to join the leaderboard, I will leave the leaderboard code in the description. And thank you for watching. Happy holidays, and see you tomorrow.